Hi pre-calc class, I'm so sorry I'm out today, but I made a quick video to help you with the rest of 1.1. So we're going to talk a little bit more about the difference between, let me write there, the difference between regular sequences, just plain sequences, and then arithmetic or geometric sequences. So if you remember from the other day, we talked about what an arithmetic sequence is, and it was any sequence that had an adding pattern. So we want to start to analyze these to help us create some equations of these functions eventually. And today the only goal is to figure out, is it arithmetic? Okay. So I'm looking at the sequence I gave you, 12, 9, 6, and 3, and I said, okay, well from 12 to 9, I am taking away 3, or I'm going to think about it as adding negative 3. So 9 to 6, I added negative 3, 6 to 3, I added negative 3. That pattern has to hold true for the entire sequence in order for it to be considered arithmetic. So if the value is the same all the time, we call that our common difference. And we represent that usually with the letter D. So D is negative 3 here. That'll have significance for us in a minute, but for right now, we're just identifying that value. The second sequence is 1, 3, 9, 27, and 81. Right now, I am looking at the pattern, and I can't figure out if I'm adding the same value every time, but I do notice that to get from 1 to 3, I multiplied by 3. 3 to 9, I multiplied by 3, 9 to 27. So that's actually a pattern of multiplication, which makes this a geometric sequence, not an arithmetic sequence. So that multiplication value, we call that the rate of increase or decrease. So in this case, we would say R is equal to 3. There are some formulas that we'll go over next time that help us create the equations for these functions. Today we're just going to kind of think about it on our own, but D and R become really important when we start to use those formulas. So I'm going to step over into maybe Desmos right now. So you can see I've taken the data that you have here and input it into some tables in Desmos. So the X column, that is our input value, like N. So I went 1, 2, 3, 4 with this first sequence here. And so we just went, that's my first term, second, third, and fourth. So then I entered the output values over here, 12, 9, 6, and 3. And if you look, they're generating these 4 points, right? So you're looking at that and trying to decide maybe what type of function would that be. If it's 4 points and they all look like they have the same increase or decrease, then we can say that this type of sequence, an arithmetic sequence, is really creating a linear function, all right? It's called a discrete function because it's made up of separate points and they're not connected. You might have heard that when you talked about domain and range before. Discrete functions means that those are separate points. And the linear function model that we usually talk about is y equals mx plus b. If you remember from Algebra 2, you could use like a regression line to figure out the equation here. But we're just going to use our noggins. So if I go back and I try and look at, okay, what might be the y-intercept here? If I follow that same pattern, looks like it's going to be 15. And the slope is down 3 over 1 every time, negative 3x plus 15 is my function. So that right there would be an equation that models this sequence. And that negative 3, the slope, is coming from the common difference, right? That's what you're really finding. Linear functions have the same rate of change. So negative 3, if that's the common difference, that's what I'm subtracting every time, or adding, rather, then that's the slope. And then 15, if we look at this table, right, when n was 1 or when x was 1, our output was 12. Well, if we went back up one value in this table, if we reverse that and said, okay, well then when x is 0 or when n is 0, what's the output? Well, it would be 15, right? If we reverse that pattern. So it would be really 15, 12, 9, 6, 3. So that 0th term that we normally talk about is really the y-intercept. And that's true of all functions, not just the arithmetic sequences, okay? So let's switch gears here and we'll look at the second set of data. So I input that, again, my n values are 1, 2, 3, 4, 5. My output's 1, 3, 9, 27, and 81. And then taking a look at this function here, we can see that we're getting an exponential function. So anytime you get that pattern of multiplication, it's creating an exponential function for you. And usually the equation for that is y equals a b to the x. B is the base. That's our sort of our rate of change. So every time we go over to the next value on this exponential function here, every time you go over to the next integer, you see that the value is tripling, right? It was at 1, then it's at 3, then it's at 9, then it's at 27. So that rate of increase has to be 3. So we know we're looking at 3 to the x. But if you try it out, let me get rid of this for a sec. If you tested that out, to see if you actually got these values, when you put in 1 for x, you would end up with 3. But really what you want to end up with over here is 1. Oops. Sorry. Is 1. So we want to figure out, okay, then how do we take 3 to the x and get 3 but actually turn it into 1? Well, you could do a few things, but one of the things I might think of is divide it by 3, or that's the same thing as multiplying by a third, right? So if I really took 3 to the x and divided it by 3, I could clean that up a little bit and say, okay, well, this is a power of 1 in the denominator, and then what happens to my exponents when I'm dividing? I subtract. So this is actually 3 to the x minus 1 power. So if I take that as my equation, we want to see if that holds true for the rest of the terms. So let's say when I substitute in 2, right? When n is 2, I should get an output of 3. Well, 3 to the 2 minus 1 is 3 to the first, which, yeah, would be 3, right? 3 to the 3 minus 1 is going to be 3 squared, which is 9. So that's working out here. So anytime you have an arithmetic sequence, you're getting a linear function. Anytime you have a geometric sequence, you're going to get an exponential function. You guys know a little bit about these already, and you can use your sequencer to help you figure those out. Today, all you have to do is identify what's what, but eventually we're going to start to create these formulas more often. Okay, so that's the first piece I wanted to look at today. The second piece is some factorials. So let's get down here. So we are going to talk about some factorials, that little exclamation point. Yes, you can use your calculator, but for right now, we're going to say no calculators, and I want to talk about how to expand it first, because I think, honestly, that's a simpler way to figure these out. So let's start with maybe 6 factorial divided by 8 factorial. If you remember from the other day, factorial means that we're multiplying the value by all the positive integers less than that down to 1. So 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. All right. 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? So once I see that, if you have any factors over each other, that are all lined up, you can start canceling those out because 6 divided by 6 is really just 1, right? So as long as it's connected with multiplication, go ahead and cancel. All of those things cancel and you end up with 56 in the denominator and then a placeholder of 1 in the numerator. So that whole thing simplified down to 1 over 56. You cannot cancel out just the exclamation point. So I can't do that up here and try and get 3/4. But you can expand it out and cancel factors, right? So I want you to pause the video and see if you can figure out 12 factorial divided by 9 factorial. So take a minute on your own, see if you can figure that out. And then when you come back, unpause, and I will do it out for you. So up here, it's 12 times 11 times 10 times 9. And I could go all the way down to 1, but I actually am going to stop there because I see that down here we have 9 factorial. And those two things are matching up. They have all the same factors. Just like up above, 6 factorial, this entire thing was embedded right here. So I could have stopped up top. I could have left the numerator as 6 factorial and the denominator just done 8 times 7 times 6 factorial and canceled them out right from the get-go, okay? So I'm going to do that same thing here. It's 12 factorial divided by 9 factorial. Boom, 9 factorial disappears, and I'm left with 12 times 11 times 10, which I think is 1,320. I might be wrong about that. I'll double check in a sec. But that idea there, you would just multiply these values out, okay? No, that's right. Okay, so let's get a little more abstract now. Let's talk about just n factorial, right? If 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, then n factorial must begin with n. And then we're going to multiply it by a value that is 1 less than that. So if we started with 6 and the next one's 5, if I start with n, then the next factor must be n minus 1, because we took away 1 from the original value, right? If that was 6, then that's 5. The next value would be n minus 2, because if you start with 6, go 2 spaces down, you get to 4, so you're taking away 2. And then n minus 3, n minus 4, and so on. And this could go on infinitely until you get to 1, so you can use the little ellipsis there down to 1. So maybe I give you n plus 2 factorial divided by n minus 1 factorial. All right. I'm going to choose the larger factorial, and I'm going to expand it out until I hit the smaller factorial. So n plus 2 factorial is the larger one. So we're going to start with n plus 2. And then the value that is 1 less than that would be n plus 1, right? N plus 2 minus 1 is n plus 1. And then n plus 1, the one lower than that, would just be n. And then n minus 1, and oh, that's where I find this, right? So I'm going to stop there and do n minus 1 factorial, and the factorial is only attached to what's directly next to it, so it's only attached to the n minus 1. Since that shows up in my denominator as well, I can cancel those out, and I'm just left with n plus 2 times n plus 1 times n, okay? You could multiply that out if you want to. You do not really need to spend time doing that. You can leave it in its factored form. But that would be your answer. All right. So I hope this helps you finish the rest of your assignment. In Schoology, I would like you to complete these 4 graphs, so 33 to 36, part of the red problems up here. I would then like you to try these problems written in red. 1, 4, 5, 12, 13, 16. And then lastly, these couple factorial problems, okay? If you need help, please email me and I'll be happy to help. There are some notes attached from my class on Monday, so you can look at those if you need to. And I hope you have a wonderful class.